Thank you so much for your insight. It's also very helpful to hear about like what sort of ways you have interacted with the theorem in the past and how it has applied in like sort of like industry. I guess like what you said earlier about discussing more after you've read the paper. I think that's probably a better idea because there were some questions I had about the I guess models they proposed in the paper that I really want to get your idea about. For example, this kind of like active inactive like receptor switch and the probability distribution of receptor configurations. And just as a quick aside, I got interested in information theory after reading Jack Monod's book on chance and necessity, where he talks a lot about allosteric
Excellent. Yes, Monod. Oh, yeah. Excellent. I'm impressed.
It's a super like I mean it's kind of old-ish now, but it's a really good book, and that's how I got introduced to Maxwell's demon and this kind of like changing of like I guess in this case chemical energy into information, because the function of the protein is encoded I guess in the sequence and it folds, and then this conformation change that kind of gives rise to the various responses that we see in cells. So and there's also a lot more that I'm still trying to learn since I don't come from this background about kind of how much like the information can pass through a membrane at a given time, how that's like modulated, and we see this like binding, or how much can this like even just at a single cell sort of level, how much can really be reliably like transmitted, and also between different receptor conformations, what like in terms of mutual information, how much distinct I guess information or encoding can be distinguished by the cell. So that was really something that we lould look forward to like discussing more with you and see what you think about that.
Interesting. So may I ask, what is your training?
My training, so I did a lot of experimental pharmacology. So I came from a very like strongly experimental background. I was introduced to GPCRs in the wonderful world of pharmacology and shape-shifting proteins when I was doing my bachelor's in New Zealand under Professor Michelle Glass, who also introduced a lot of like kinetics. We like read your review as kind of like the paper to study, and I have been following your theories and models since. But then when I did my master's at UCL, where you also worked, I think, I was introduced to systems biology, just kind of as a better way to model maybe more holistically kinetic responses in cells, and that's what I did my PhD on. So combining.
Excellent. I was interested in the abstract of the article. You expect on-off switches. I wasn't sure about the intermediate switch. What is that? So I'll read it and we'll talk about it. But this leads us into your second question, which was related, and I'll see if I can get that. What are some good ways to quantify and model the oscillating events of endogenous ligand and the allosteric modulator? Good question, because now that we're looking for therapeutic PAMs to revitalize failing systems, this is really an issue. So what are those to achieve best therapeutic effects at a cellular level? What is PBPK, Kylie? I'm sorry, what?
Yeah, so I should explain the acronym. So that's, I think, physiologically based pharmacokinetic modeling.
Oh, okay, good. Got that. Okay, so yes, what you put forth is actually a very important thing in therapeutics now. We're good at finding compounds, characterizing them in a system that we can control, and then we let them loose in Vivo, and that's an uncontrolled system. All kinds of things can happen. It's up to us to try to anticipate what those will be so that we can choose the right compound. When you're dealing with allosteric, we all know there's great reasons why you should go for an allosteric, but it also begs this question. If you have a pure NAM or a pure PAM, it will only do things in accordance to what the system's doing. Then it won't. I was working on a program. It was a brilliant idea how to make an analgesic, an opioid analgesic in the brain that simply potentiates the endogenous um, transmitters there. Um, and they had a terrible time trying to assess efficacy. So now, well, how do I know with this guy's brain what the levels are and what the change? So yes, it is an issue. You have this varying baseline playing field that you're trying to um, alter. So, and that's why translation of things like bias and allosteric are so difficult. We can get these compounds, they look great in our hands in controlled systems, and then they do so. The only way I've approached this so far, but there may be people I could aim you towards who would expand this, would be to use pharmacology to account for the difference in sensitivity, the difference in the way cells process the signal your compound's going to give. You will have one system and you will quantify efficacy, affinity, and so forth. But as your compound goes into different organs at different set points of sensitivity, of different receptor expression levels, it's going to give a different profile. Pharmacology is unique. It can actually account for a lot of that. And I talked about this and where if you can model in one system, then you can use that model to make predictions. And you predict, okay, if this goes into a more sensitive cell, this will happen, that'll happen. That's about the best we can do. The PK aspect, yeah, if you can get a handle on what your endogenous transmitters and hormones are doing, that would be a huge thing as well. And I've been involved in modeling that, where the company actually had a method to say, this is where this hormone is at this point. What's going to happen with my compound? Well, if you have that piece of cake, the same model that modeled differences in sensitivity can model differences in levels of transmitter and hormone and so forth. Having said that, I've likened the translation to whole cell in vivo levels to working with Enigma. Enigma, if you don't know, it was the coding machine that Germany had during World War II, and it was able to generate something like 160 billion codes, and it was impossible to crack. And the British did it though, but it was and you can actually model from your little cell, this molecule is biasing to this, and then go through the Enigma steps. It was a series of wheels that coded things. By the time you get in Vivo, you have millions of potential options, and that's going to be our challenge. The only advice I have, and I'll stop then, is to say, get your molecule, identify the exemplar. All these assays, all they do really, I doubt they'll predict what will happen, but they'll identify the unique probe for you. This molecule makes a unique active state. And then go into the natural system as soon as you can, because only then will that translate. What does that mean? A lot of people argue, well, all these bias assays look at beta-arrestin and cyclic AMP, calcium. What if I don't care about those? And I say, no, that's not the point. You're not trying to model what you think will happen. Those are tools that simply tell you the molecule that makes a weird state, as opposed to the natural hormone transmitter. That's all it does. And you can use anything beta-arrestin, calcium, GS, GQ, doesn't matter because you're using those systems to decode what this molecule makes of your receptor. Beyond that, take it into the natural state and see. So, again, I haven't given you any magic method, but at least suggest that it's not worth going through endless in vitro models of bias and so forth to try to predict what will happen. Get a model, and then, as Stephen Hawking said, let the model unveil the universe of options that could happen. So I don't know if I've answered your question, Kylie. You tell me what else is interesting to you.
Oh, I really like the part where you talked about how it's like using these like probes, or they're like tools for kind of probing and sort of deciphering a little bit of like how the cells make sense, I guess, of like the extracellular sort of size. To kind of like backtrack a little bit, my interest is also a little bit more now leaning towards like understanding exposure at sort of cellular or like organ level, as we were sort of you also alluded to earlier, because I think all is nice about like in a plate or in a dish where you can control much more or kind of keep constant, I guess, the orthosteric probe and your allosteric probe. But then I guess like my question was more also, or sort of my lines of thinking were kind of like if the endogenous hormone also like cycles through having like troughs and like peaks, and then you have like a drug that also has, you know, different like penetrations, elimination and such, how can it be dosed, or is there some, it's more kind of like exploring the ways to like understand if there's a good dosing regime that can keep it at like a level that's able to like propagate these like beneficial like effects that we want to see or have.
Good point. You raise an interesting point. Thank you. Because there is something else you can do. And I'll make the point that unlike orthosteric compounds, allosteric effects are saturable. So you can, if you put an orthosteric antagonist in there, the duration of action is linked to how much you give. And that's the intensity of effect. So you want a long acting, and you get a high dose, and you get an overdose. Allosterics, the allosteric effect stops when the allosteric site is full. That's it. So you can make an allosteric pen that potentiates sixfold and no more than that. You'll never get more than that. Then you can load up the system PK-wise, just give a huge dose. You won't cause an overdose, but you will increase duration, and that's the beauty of it if you can get that right. For example, calcium. There are cases where you might have a need to potentiate the calcium sensing signal, and companies work on that. There are compounds that potentiate calcium, but cells hate calcium. It's toxic. They go through all kinds of ways to limit free calcium, and so some of these potentiators had toxic effects. One or two didn't. There is one that produces a 2.5 to 3-fold potentiation only. It's perfect, no overdose, and that's the approved drug, cinacalcet. See, so you can in your program say, well, I don't know what PK will be. You know, my effect will wane with levels, of course, but I can perhaps give myself a cushion here. If I can limit my effect, then I can push PK and get rid of some of that movement oscillation. And so, for example, a friend of mine was working with a company for muscarinic I think it was M4 receptor potentiation for improving cognition in schizophrenia. And they went with their most powerful PAM, and it gave like 200-fold potentiation. And guess what? They saw cholinergic side effects. And my friend who knew this said, no, choose your weaker compound, choose your less efficacious. And I don't know what happened, but that's the idea. The other thing that your question raised, and I forgot to mention this, is one other reason translation could be so hard as we go to a complicated physiology with our simple probe. This was unveiled in a speech by my old boss, Sir James Black, in his Nobel lecture. And it's printed, you can read it. And it's a beautiful description of the way he saw translation. He says, physiology, it has been engineered with a multiple array of steps. There's not one controller. You might want to inhibit or turn on a number of these. So it's difficult to have one drug fix the whole system because it's so complex. And he made a point. He said, what if I had a bunch of drugs that just tweak each one of these? The sum would be what you want. And of course, that leads to all kinds of questions. But that was his way of saying it might be a lot harder to modify a system, which we are trying to do, than we think with just one drug. We'll see. Anyway, what else do you have on that, Kylie?
Oh, thank you so much for your response, and I also really like that you finished on your response on the sort of like systems perspective. And also, I feel like that's indeed true. Just applying through like literature, also hearing other people's challenges and problems when trying to develop drugs. It's like trying to modulate like such a big and vast and complex thing.
Yeah, I got interested in this when I read and started reading more about that the attrition rate of candidates is between 50 to 80% due to efficacy. I was stunned. That's a terrible outcome. The drugs don't work. That's not safety. That's not all the other reasons drugs fail. You just made a drug that didn't work. You had a team of 30 people working 5 years, spending millions of dollars, doing everything you knew how to do to make the right compound, and it failed. So there's a big gap here. And so discussing this translation issue really has become important, and will be.